For centuries, humanity has gazed at the night sky, wondering about the origins of everything. The Big Bang theory, the dominant explanation for how our universe began, tells us that space, time and matter all emerged from an unimaginably hot and dense singularity nearly 13.8 billion years ago. But this explanation leads to an even deeper question. What came before the Big Bang? Did time and space exist before this moment, or did they emerge with it? Was there another universe that gave birth to our own? Could the laws of physics themselves have been different before the Big Bang? Scientists and philosophers have long debated this mystery, and while no definitive answers exist, modern physics offers fascinating theories that attempt to peer beyond the cosmic veil. Some suggest that our universe is just one of many, part of a vast multiverse where Big Bangs happen endlessly. Others propose that the universe has no true beginning, that time is cyclical, with universes collapsing and rebirthing in an eternal loop. Still, others believe that quantum mechanics holds the key, with tiny fluctuations giving rise to the cosmos from what appears to be nothingness. Even religious and philosophical perspectives offer intriguing insights into the nature of existence before the dawn of time. Exploring what came before the Big Bang is not just about answering a scientific question, it is about understanding our deepest origins, the nature of reality itself, and whether we will ever be able to unlock the secrets of what happened before everything began. The Big Bang theory revolutionized our understanding of the universe. But how did we arrive at this idea? For much of human history, people believed the universe was eternal and unchanging. Ancient civilizations, from the Greeks to Hindu scholars, had various cosmological models, many of which suggested that the cosmos had always existed in one form or another. However, this perspective began to shift in the early 20th century when astronomers discovered something extraordinary. The universe was expanding. In the 1920s, Edwin Hubble's observations of distant galaxies revealed that they were moving away from us, meaning that space itself was stretching. This led scientists to reverse the process mathematically and conclude that the universe must have started from a much smaller, denser state. Around the same time, Georges Lemaitre, a Belgian physicist and priest, proposed what would later become the Big Bang theory, suggesting that the universe began from a primordial atom that rapidly expanded. The idea gained further support when, in 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, the faint afterglow of the Big Bang. This provided strong evidence that the universe had a hot, dense beginning. Over the decades, advances in observational cosmology, including measurements of cosmic expansion, large-scale structures, and the distribution of galaxies, confirmed the Big Bang as the best explanation for the origin of the universe. Yet, while the theory explains how the universe evolved from a singularity, it does not tell us what caused it or what, if anything, came before it. This limitation has led scientists to search for deeper theories that go beyond the Big Bang, ones that might explain the origins of time, space, and the fundamental laws of physics themselves. While the Big Bang theory explains the evolution of the universe from a hot, dense state, it leaves several unanswered questions, most notably what happened before it. The biggest limitation of the theory is that it breaks down when approaching the singularity, the point where all matter and energy were compressed into an infinitely small space. At this scale, the laws of physics as we know them cease to function, and both general relativity and quantum mechanics struggle to describe what occurred. One key issue is that the Big Bang does not necessarily describe the actual beginning of everything. Rather, it marks the point where our current understanding of physics can no longer trace events further back. If we attempt to rewind time beyond this singularity, the equations of general relativity give nonsensical results, meaning that our knowledge is fundamentally limited by the tools we currently have. This is why many scientists believe that new physics, such as a quantum theory of gravity, is required to make sense of what came before. Another limitation is that the Big Bang theory does not explain why the universe began expanding in the first place. It describes what happened after expansion started, but does not tell us what triggered this event. If space and time emerged from a singularity, what caused this transition? Did something exist beforehand to set it in motion? Or did the laws of physics themselves emerge along with the universe? Furthermore, the idea that the universe came from nothing is often misunderstood. In physics, nothing does not necessarily mean an absolute void. It could refer to a quantum vacuum, fluctuations in a pre-existing field, or even a timeless state from which space and time emerged. This leads to a variety of competing models that seek to explain what came before the Big Bang, each offering a different perspective on the nature of existence before our observable universe began. To push beyond the limitations of the Big Bang theory, scientists have turned to new cosmological models, including quantum mechanics, cyclic universes, and the multiverse. These theories attempt to explain whether time had a beginning, whether our universe is one of many, and whether physics itself existed before the Big Bang. Understanding these ideas brings us one step closer to uncovering the deepest mysteries of our origins. One of the most profound questions in cosmology is whether time and space themselves began with the Big Bang, or if they existed before it. In Albert Einstein's theory of general relativity, space and time are woven together into a single entity called space-time, which is shaped by the presence of matter and energy. According to this model, space-time itself emerged from the Big Bang, implying that there was no before in the traditional sense. Time simply did not exist prior to this event. However, some physicists challenge this idea, arguing that the concept of before the Big Bang may still be meaningful under certain conditions. Quantum mechanics introduces uncertainty at the smallest scales, suggesting that space-time could have undergone fluctuations before the classical expansion of the universe began. If time and space were subject to quantum effects, they might have existed in a different, unrecognizable form before transitioning into the expanding universe we observe today. Another perspective comes from loop quantum gravity, a theory that attempts to merge general relativity with quantum mechanics. This model suggests that instead of a singularity, there may have been a quantum bounce, where a previous universe contracted to a small but finite size before rebounding into our expanding universe. In this scenario, time would extend infinitely in both directions, meaning the Big Bang was not an absolute beginning, but rather a transition from one phase of the cosmos to another. Other theories suggest that time might be an emergent property, meaning it did not exist before the Big Bang in a traditional sense, but crystallized from a more fundamental timeless state. Some physicists propose that what we perceive as time may arise from deeper laws of quantum physics that we do not yet fully understand. Ultimately, whether time and space had a beginning or existed eternally before the Big Bang remains an open question. Quantum mechanics, the branch of physics that governs the smallest scales of reality, offers intriguing possibilities for what may have come before the Big Bang. Unlike classical physics, which assumes that objects have definite properties, quantum mechanics introduces uncertainty, probability, and spontaneous fluctuations, all of which may have played a role in the birth of our universe. One of the most promising ideas comes from quantum fluctuations, which suggest that even in what we perceive as empty space, tiny particles and energy fields constantly pop in and out of existence. If the universe emerged from such fluctuations, it might mean that nothingness is never truly empty, but rather a seething, dynamic quantum state filled with potential energy. This raises the possibility that our universe could have spontaneously arisen from a pre-existing quantum vacuum without violating the laws of physics. Physicists like Stephen Hawking and James Hartle have proposed that space and time may have been governed by quantum mechanics at the very beginning. Their no-boundary proposal suggests that before the Big Bang, time behaved more like space, meaning there was no distinct before in a classical sense. Instead, the universe smoothly transitioned from a quantum state into the expanding cosmos we observe today. Another concept linked to quantum mechanics is the idea of a pre-Big Bang state, where tiny energy fluctuations eventually triggered cosmic expansion. These fluctuations might have been incredibly small, but under certain conditions, one could have led to a runaway effect, creating the hot, dense state that initiated the Big Bang. This idea aligns with the broader principle that quantum uncertainty allows seemingly impossible events to occur given enough time. While these ideas remain speculative, they highlight an important shift in how we view the origins of the universe. Instead of needing an external cause or divine intervention, the principles of quantum mechanics may be sufficient to explain how something can emerge from nothing. However, whether this nothing is truly nothing or simply an unfamiliar quantum state is still an open question, one that future discoveries in physics may help answer. The idea that our universe was not the first but rather part of an eternal cycle of cosmic births and deaths has fascinated scientists and philosophers for centuries. One of the most compelling alternatives to a singular beginning is the cyclic universe hypothesis, which suggests that universes have been expanding and contracting in an infinite loop, with each cycle giving rise to the next. This idea challenges the notion that the Big Bang was an absolute beginning. Instead, it proposes that our universe is the latest in a series of expansions and contractions where each cycle ends with a big crunch, a scenario in which the universe collapses under its own gravity, only to be followed by a new Big Bang. This would mean that time stretches indefinitely into the past and future, eliminating the need for a singular starting point. One modern version of this idea comes from the ekpyrotic universe model, which is based on string theory. This model suggests that our universe is a three-dimensional brain floating in a higher dimensional space. According to this theory, the Big Bang was caused by the collision of two such brains, which could have happened countless times before. Each collision would trigger a new cycle of cosmic evolution, making our universe just one chapter in an infinite cosmic history. Another cyclic model involves quantum bounce theories, particularly those inspired by loop quantum gravity. This theory suggests that instead of collapsing into an infinitely small point, a previous universe may have reached an incredibly dense but finite state before rebounding into a new expansion phase. In this case, the laws of quantum mechanics prevent the singularity from forming, ensuring that the universe never truly reaches a point of absolute destruction, but instead cycles endlessly. If the cyclic universe hypothesis is correct, it could explain why our universe appears so finely tuned for life. If countless universes have existed before ours, then natural selection on a cosmic scale may have favored universes with conditions that allow for complexity and stability. However, this idea also raises deep questions. If universes are cyclic, what governs these cycles? Is there an underlying mechanism that determines when one universe ends and another begins? And most importantly, if universes have been cycling forever, what was the very first cause, if there ever was one? Yes. While the cyclic model remains speculative, it offers an exciting alternative to a universe with a single beginning. If proven true, it would mean that the Big Bang was not the birth of everything, but just another step in an eternal cosmic dance. Another fascinating possibility is that our universe is just one of many in a vast and possibly infinite multiverse. This idea suggests that instead of a singular beginning, our universe may have emerged as part of a much larger cosmic structure where countless other universes exist, each with its own laws of physics, dimensions, and histories. One version of the multiverse theory comes from eternal inflation, an extension of the inflationary Big Bang model. According to this idea, the universe underwent an extremely rapid expansion in its earliest moments, but instead of stopping everywhere at once, inflation might still be occurring in distant regions beyond our observable universe. In this scenario, our universe is just a single bubble in an endlessly inflating cosmic foam, where new universes continuously form in other bubbles. each potentially with different physical constants and properties. Another possibility is the quantum multiverse, which arises from the many worlds interpretation of quantum mechanics. This theory suggests that every quantum event results in a branching of reality where multiple versions of the universe exist simultaneously. If true, it means that what came before the Big Bang may depend on which universe you observe. Each one could have a different origin story based on its quantum history. String theory also provides a framework for a multiverse through the concept of extra-dimensional space. In some versions, our universe could be just one of many three-dimensional brains floating in a higher dimensional space, occasionally colliding to create new universes. These interactions could trigger Big Bang-like events repeatedly, meaning that universes may be constantly forming in an interconnected cosmic web. The multiverse idea is intriguing because it could potentially explain the fine-tuning of our universe, why the physical constants are just right for life to exist. If countless other universes exist with different properties, then it is not surprising that at least one like ours has the perfect conditions for complex structures to form. However, the multiverse also raises deep philosophical and scientific questions. If other universes exist, can we ever observe or interact with them? If our universe was born out of a larger multiverse, what governs its creation? Since we cannot directly see beyond our cosmic horizon, testing these ideas remains an enormous challenge. Despite the lack of direct evidence, the multiverse hypothesis offers a profound shift in how we think about the origins of reality. If true, it means that the question of what came before the Big Bang may not have a single answer. Our universe might be just one in an infinite cosmic landscape, with new universes constantly being born. The concept of a universe emerging from nothing is one of the most perplexing ideas in modern physics. When scientists discuss the idea of nothing, they do not necessarily mean an absolute void, devoid of existence, but rather a state where space, time and matter as we understand them did not yet exist. Some physicists propose that the universe could have arisen from a quantum vacuum where energy fluctuations in an otherwise empty state triggered the birth of space and time. One leading theory is quantum creation, which suggests that even in a state of nothingness, quantum laws could still apply. In quantum mechanics, particles constantly appear and disappear due to fluctuations in energy fields, even in the absence of a traditional environment. If similar fluctuations occurred on a grand scale, they might have spontaneously given rise to an entire universe. The idea is that space and time themselves could be emergent properties that arose from a deeper quantum reality. Another perspective comes from the no-boundary proposal formulated by Stephen Hawking and James Hartle. According to this model, space and time were never truly separate before the Big Bang. Instead, time behaved more like an additional dimension of space, meaning there was no distinct before in a classical sense. This smooth transition from a timeless quantum state into an expanding universe avoids the problem of an initial singularity and suggests that asking what came before may not be meaningful in the way we intuitively think. Some physicists also propose that the laws of physics themselves emerged with the universe rather than existing eternally. If the fundamental laws, including quantum mechanics and gravity, were not present before the Big Bang, then there may have been no need for a prior cause. Our universe could have simply emerged from a deeper, lawless state where existence and non-existence were interchangeable. These ideas challenge our deepest assumptions about reality. If the universe truly emerged from nothing, does this mean that existence is inevitable? Could universes be constantly forming in other quantum fluctuations across an unseen cosmic landscape? And if everything, including time and space, came into being spontaneously, does that mean our understanding of causality itself is limited? While these questions remain open, the idea that the universe could emerge from nothing is not as paradoxical as it first seems. If the laws of quantum physics allow for particles and energy to arise spontaneously, then perhaps the birth of the entire universe was just an extension of this natural process. An event where nothing was unstable, and the result was everything. As we explore these deep cosmological theories, one final question lingers. Can we ever truly know what came before the Big Bang? While physics has provided a variety of models, cyclic universes, quantum fluctuations, the multiverse, and the idea of emergence from nothing, none of them have been definitively proven. The fundamental challenge is that our ability to observe and test these ideas is severely limited. The Big Bang marks the boundary beyond which light and information cannot travel, meaning any evidence of a pre-existing state may be permanently hidden from us. However, scientists are not without hope. Advances in cosmology, quantum physics, and gravitational wave astronomy may provide indirect clues about what came before. For example, studying the cosmic microwave background radiation, the afterglow of the Big Bang, may reveal subtle patterns or anomalies that hint at a pre-Big Bang universe. Similarly, if evidence of a cosmic bounce were found, it could support cyclic universe models. Future discoveries in quantum gravity may also help bridge the gap between quantum mechanics and general relativity, potentially offering a more complete picture of cosmic origins. Another promising approach is the study of primordial gravitational waves, ripples in space-time that could have been generated in the earliest moments of the universe. If such waves contain signatures of a previous cosmic phase, they might provide the first tangible evidence of what came before our universe. Philosophically, the question of before the Big Bang forces us to reconsider our understanding of time and existence itself. If time began with the Big Bang, then asking what came before may not even be a meaningful question in the traditional sense. Instead, the universe may have emerged from a state where time did not exist, or it may be part of an infinite cosmic cycle, where the concept of a singular beginning is unnecessary. Ultimately, whether we will ever uncover the truth about what preceded the Big Bang remains one of the greatest mysteries of science. While we may never have direct evidence of a prior state, continued exploration of the universe's deepest laws might bring us closer to understanding our true cosmic origins. Whether our universe is part of a larger multiverse, the latest phase in an eternal cycle, or the product of a spontaneous quantum event, one thing is certain. The journey to uncover the origins of everything is far from over. The question of what came before the Big Bang is one of the most profound mysteries in science, pushing the boundaries of our understanding of time, space, and reality itself. While we may never have a definitive answer, the theories proposed by physicists, ranging from quantum fluctuations and cyclic universes to multiverse models and emergent laws of physics, offer intriguing possibilities that challenge our traditional notions of existence. Each theory presents a different vision of the cosmos. If the universe arose from quantum fluctuations, it suggests that nothingness is an unstable dynamic state. If the universe is part of a cycle of expansions and contractions, then time may stretch infinitely backward. If we live in a vast multiverse, then our Big Bang may have been just one of countless others. And if time itself emerged with the universe, then the concept of before may not even apply in a meaningful way. While direct evidence for these ideas remains elusive, future discoveries in quantum physics, cosmology, and gravitational wave astronomy may bring us closer to understanding our ultimate origins. The quest to unravel what came before the Big Bang is not just a scientific pursuit, it is a fundamental human endeavor to understand our place in the cosmos. No matter what the answer turns out to be, exploring this mystery deepens our appreciation of the universe and the intricate forces that brought it into existence.